When hundreds of pounds of explosives detonate directly beneath the floorboards of a military transport, standard armor won't save the people inside. Welcome to Global Warwatch Network. Mine-resistant ambush-protected vehicles, or MRAPs, shifted the focus of battlefield transport from agility to surviving those upward blasts. If you find this breakdown helpful, please subscribe. You cannot build a vehicle to shrug off explosions without piling on thousands of pounds of heavy steel armor, and that creates a massive physics problem. This infographic lays out 4 specific approaches to solving that problem: the Russian Ural Typhoon, the Canadian Shrek 1, and the American Cougar and Buffalo. Each represent a distinct national engineering philosophy on keeping troops alive. We are going to compare their mechanical trade-offs to see exactly what happens to physical footprint, engine power, speed, and operational range when you add all that armor. In MRAP engineering, there is no perfect solution, only a strict triangle of compromises that dictates how a military force operates on the ground. The baseline job of any armored transport is moving human assets safely across hostile territory. This horizontal bar chart compares the personnel capacities of our 4 vehicles. The Russian Ural Typhoon takes a massive lead here, built to haul a crew of 2 plus 14 additional personnel. By comparison, the Canadian Shrek 1 holds 10 passengers, and the American Cougar carries up to 8. On the extreme opposite end of the chart, the American Buffalo drastically shrinks its passenger space, fitting only 4 personnel. Hauling 14 people carries an immediate physical cost. Looking at the spec sheet, the Typhoon stretches to 9 full meters. A vehicle that long will struggle to navigate tight urban environments compared to shorter trucks like the Buffalo. The Buffalo makes the opposite choice. By cutting passenger space, engineers freed up the chassis weight limits to mount incredibly heavy, specialized tactical equipment, like this massive articulated robotic arm used for handling explosives. Maximizing raw troop transport capacity directly compromises a vehicle's agility and its ability to carry heavy frontline ordnance gear. Protecting those passengers requires tons of exterior steel. But once an ambush starts, that vehicle still needs to accelerate quickly enough to escape the kill zone. This scatter plot maps engine horsepower against vehicle mass. It shows a clear principle. To maintain highway speeds with heavier armor, you have to drastically upsize the engine. Look at the Buffalo. It represents the extreme upper limit of this philosophy, weighing a staggering 36,000 kilograms. Despite carrying all that mass, it uses a 450 horsepower engine to tie for the highest top speed at 105 kilometers per hour. Now look at the Cougar. It weighs significantly less at 23,600 kilograms, but hits the exact same top speed. Because it is lighter, the Cougar achieves that rapid deployment much more efficiently, needing only a 330 horsepower engine. There is an anomaly in the data, however. The Canadian Shrek 1 is the lightest vehicle we're looking at, weighing just 16,000 kilograms, yet features the exact same 330 horsepower engine as the Cougar. Yet it yields a surprisingly low top speed of just 80 kilometers per hour. This indicates a strict engineering choice to prioritize low-end torque and stability over rapid highway deployment. Pushing the Buffalo's 36,000 kilograms to 105 kilometers per hour comes with a severe hidden cost. Achieving that momentum with massive weight causes immense mechanical stress and burns through fuel rapidly. Manufacturers can compensate for massive weight by dropping in larger engines, but achieving high momentum with extreme mass requires devastating compromises in fuel efficiency. That brings us to our final metric, operational range. This number dictates how deeply a vehicle can penetrate hostile territory before it has to rely on vulnerable fuel supply lines. This descending bar chart tracks operational range, and the Russian Ural Typhoon dominates the category, capable of traveling 1,800 kilometers on a single tank. That is nearly double the range of the second-place Canadian Shrek 1, which covers 1,000 kilometers. Pushing a heavy truck for 1,800 kilometers requires hauling the massive weight and volatility of a huge liquid fuel payload over long distances. Here we see the true consequence of the Buffalo's high-mass, high-speed engineering. It possesses the lowest operational range, topping out at just 485 kilometers. Even the Cougar, running a moderate middle ground, outpaces the Buffalo's short sprint capacity with a 670-kilometer range. Distance endurance is the very first casualty when engineers prioritize slapping on the heaviest possible armor and demanding rapid acceleration. Prioritizing range defines the MRAP as a long-haul survival transport, while prioritizing armor mass limits it to short-burst, highly localized operations. You cannot rank these vehicles from worst to best. They have to be mapped to the exact tactical missions they were built to dominate. This quadrant chart plots range and endurance on the x-axis against speed and mobility on the y-axis to give us a clear tactical matrix. The American Cougar and Buffalo sit in the high-speed, low-endurance quadrant, reflecting a philosophy of rapid response and brute force protection. The Russian Ural Typhoon lands out in the extreme high-endurance quadrant, built for sustained, long-distance personnel transport. And the Canadian Shrek 1 anchors near the center, offering a balanced middle ground approach. If your mission demands moving a large squad safely across a vast 1,000-kilometer territory, the Ural Typhoon is the optimal tool. But if you need the absolute heaviest armor driving rapidly for short bursts into localized danger, the Buffalo is your definitive choice. Thank you for watching Global Warwatch Network. Let us know in the comments which engineering philosophy you think makes the most sense on the ground. And please remember to like, share, and subscribe.